Welcome back to the Deep Dive. Today we're going to delve into some really fascinating research, specifically on video super resolution. We've got this paper on a novel approach called STAR, which stands for Spatial-Temporal Augmentation with text-to-video models for real-world video super resolution.
Yeah, it's quite a mouthful.
It is quite a mouthful.
But essentially what it is a technique for taking low-resolution videos and making them much sharper, making them clearer, even when those videos are blurry or degraded in a number of different ways.
And what's really interesting is they're using this text-to-video AI to do it.
Right.
But before we even get into that, I think it's worth talking about why real-world video super resolution is such a challenge in the first place.
Yeah, so traditional methods have really struggled with the unpredictable degradations that you find in real-world video. Things like noise and compression artifacts or blur. And these methods often result in videos that are over-smoothed or lack consistency from frame to frame.
So even some of these newer approaches using image diffusion models, which I know had some promise, they're not quite cutting it.
Yeah, they show potential, but they're primarily trained on static images and don't fully grasp how objects move and change within video.
So how does STAR then kind of overcome these limitations using text-to-video models?
So STAR leverages pre-trained text-to-video models. Some examples are CogVideoX and i2vGen-XL. And these models are trained on these massive data sets of text and video pairs, which gives them this remarkable ability to generate a realistic video just from a text description.
It sounds like these text-to-video models have a much deeper understanding of video than image-based models. So how are they actually applying it to video super resolution specifically in STAR?
So the researchers behind STAR, they've incorporated two key innovations. The first is the Local Information Enhancement Module, or LIEM, and they recognize that standard text-to-video models often rely on global attention. And while this works well for generating an entire video, it's not ideal for restoring intricate details in specific regions.
So it's almost like trying to fix a small tear in a tapestry by reweaving the whole thing.
Right.
You're not really addressing that specific problem.
And LIEM addresses this by incorporating this local focus. It allows the model to really zoom in on specific areas and correct those degradations region by region before considering the entire frame.
And you can really see the difference in Figure 3 of the paper, especially in the way it restores like text and fine details.
Yeah.
So what's the second innovation?
The second innovation is the dynamic frequency loss, or DF loss. And this gets at the fact that restoring video isn't just about adding details. You have to find the right balance between those fine details and the overall structure and motion of the video.
Frequencies, are we talking about sound waves here?
It's a similar concept, but applied to visual information. So you can think of it this way. Low frequencies represent the basic shapes and structure of a video, while high frequencies contain the finer details like textures and edges.
So DF loss essentially helps STAR create more natural-looking results by making sure the right level of detail is added at each stage of the restoration process.
That's right. And what's fascinating is the researchers observed that the model tends to rebuild the overall structure first, almost like building a scaffold, and then goes back and fills in those finer details.
That's a really cool approach. But, does it actually work? Does STAR actually deliver?
So the results are very impressive. They tested STAR on several benchmark data sets, both synthetically generated and real-world footage. And it consistently outperformed the existing methods based on a variety of metrics, things like PSNR, SIM, and Dover.
The numbers are great, but seeing is believing. What about those visual comparisons?
The visual comparisons in the paper, particularly figures 6 and 7, are really compelling. You can clearly see STAR's ability to recover sharp details, remove those distracting artifacts, and reconstruct complex elements like text and fur much more effectively than other methods.
Speaking of real-world video, they also used a metric called eWarp to evaluate the temporal consistency.
Yes, they did.
So what is that? What is eWarp?
So eWarp measures how smoothly objects move across frames. And STAR showed a significant improvement in this area compared to methods that rely on optical flow maps, which can be unreliable, especially in complex scenes.
So STAR, it seems like it's doing a lot. It's enhancing the detail, it's getting rid of those artifacts, and it's also ensuring that the video maintains that natural motion. Did the researchers experiment at all with those larger text-to-video models that we mentioned earlier?
Yes, they did, and this is where it gets even more interesting. They found that using larger, more powerful T2V models like CogVideoX actually produced even better results. And this suggests that the future of video super resolution might really lie in harnessing the power of these massive AI models.
So the bigger the model, the better the restoration.
The scaling law experiments indicated a clear trend. Larger models trained on more data lead to more realistic and detailed restorations. So this is a really exciting avenue for future research.
So SAR, it sounds like it represents a pretty big leap forward for video super resolution.
It's really a fascinating advancement.
So we talked about those visual comparisons, but can you elaborate a little bit on the specific metrics they use to evaluate STAR's performance?
Sure. So they use a variety of metrics that assess different aspects of the video quality. So to measure how closely the restored video matched the original high-resolution video, they used PSNR, which stands for peak signal-to-noise ratio.
So a higher PSNR score basically means a closer match to the original.
Exactly. They also use SSIM, which is a structural similarity index, and this metric takes into account the structural resemblance between the restored video and the original, which aligns more closely with human perception of quality.
So it's not just the pixel level data, but how we actually perceive those differences.
Yeah, it goes beyond just pixel comparisons to factor in things like luminance and contrast and structure. To specifically evaluate the clarity of the restored video, they use a metric called Dover, which is Deep Video Quality Evaluator.
So Dover essentially measures the sharpness and level of detail in the output.
Yes, it assesses how well-defined the details and edges are in the restored video. For real-world videos where a pristine original might not be available, they used eWarp, which quantifies the temporal consistency of the video.
So eWorld would be able to detect any jerky or unnatural motion in the restored video.
Yeah, it measures how smoothly objects move across frames. And STAR showed a marked improvement in eWarp scores compared to other methods that rely on optical flow maps, which can be inaccurate, especially in complex or challenging scenes.
It's incredible that STAR's not only enhancing the clarity and the detail, but it's also ensuring that the video maintains that natural motion.
Yeah.
Can we talk a bit more about the Local Information Enhancement Module, or LIEM? What exactly was its function within STAR?
Yeah, so LIEM is a really crucial component of STAR. It addresses a limitation that's often found in text-to-video models, which heavily rely on these global attention mechanisms.
So it's kind of like giving the AI a magnifying glass, so to speak, so it can focus on and really refine those specific areas.
Yeah, you can think of it that way. And LIEM allows the model to handle these complex degradations on a region-by-region basis, which is what results in those really accurate restorations that we were talking about. And you can see the improvements in clarity and detail in the results that they presented, particularly those shown in Figure 3.
And what about the dynamic frequency loss, or DF loss? How did that contribute to those impressive results?
So DF loss plays a critical role in balancing the restoration of fine details with the overall structure and motion of the video. It dynamically adjusts the model's focus on different frequencies of information throughout the restoration process. And they observed that low frequencies, which represent those structural elements, tend to be restored first, followed by the high frequencies that contain those finer details.
So it's almost as if the model lays down a foundation first, and then goes back and adds those finer details later.
Right. And so that's how DF loss helps to ensure that the restored video doesn't look overly sharpened or artificial and maintains that natural look and feel.
So STAR with LIEM and DF loss consistently outperformed other state-of-the-art methods across those various metrics and data sets. But let's kind of zoom out a little bit and look at the bigger picture here. Where does this research fit into the evolving landscape of AI and video technology?
I think one of the key takeaways from this research is the potential of these large-scale, pre-trained text-to-video models. As these models grow in size and complexity, they're only going to become even more powerful tools for video enhancement and generation.
So we're essentially talking about AI models that possess this deep understanding of how the visual world works. Models that can not only restore and enhance existing videos, but generate entirely new ones from scratch. It seems like the line between video restoration and generation is becoming increasingly blurred.
We're definitely seeing that trend emerge.
This is raising some really interesting questions about the future of content creation. But I think for now, we've done a pretty good job of unpacking the key insights from this research. We've talked about the challenges of real-world video super resolution, the innovative approach of STAR, and all those sophisticated metrics they use to evaluate its performance.
Yeah, and we also discussed those large-scale text-to-video models and their potential to really reshape the future of video technology.
It's clear that STAR represents a really significant step forward in the field of video super resolution. It's been fascinating to delve into this cutting-edge research.
Yeah, the insights gleaned from this deep dive have been really enlightening.
Well, on that note, we'll wrap up this episode of the Deep Dive. Thank you for joining us.
It was a pleasure discussing this research with you.
And to our listeners, thank you for joining us on this deep dive. We'll see you next time as we continue to explore the frontiers of knowledge and innovation.